54 adults. That's how many people China's new carbon fiber material can tow behind a full-sized coach, using a strand of material thinner than a single human hair. Not a special demo prop built for cameras. A real strength test on a real production material that China just became the first country on Earth to manufacture at industrial scale. And by the end of this video, you'll understand why the country that used to buy this exact material from Japan and the United States just quietly stopped needing to. Let's start with the number that should genuinely stop you, because it's not the kind of thing that gets exaggerated for a headline, it's an actual measured property. In March 2026, China's state-owned building materials giant CNBM, through its carbon fiber unit Zhongfu Shenying, announced it had reached stable industrial production of a T200 grade, ultra-high-strength carbon fiber called SYT80. The disclosed performance figures include roughly 8,000 megapascals of tensile strength, about 324 gigapascals of tensile modulus, and a density around 1.79 grams per cubic centimeter. If those numbers mean nothing to you yet, here's the translation that actually matters. That density is roughly 1/4 that of steel, while the strength-to-weight ratio is somewhere between 8 and 10 times stronger. Picture a steel cable strong enough to hold up a bridge. Now imagine cutting that cable's weight down to 1/4 of what it was, while it still holds the exact same load, or more. That's not a marginal improvement in materials engineering. That's the kind of number that makes entire industries rethink what their products should be built out of. So what is this material, actually? In plain terms, carbon fiber isn't new. It's been around in aerospace and high-end sports equipment for decades, in your golf clubs, your bike frames, the wings of a passenger jet. But not all carbon fiber is created equal, and the industry has its own strength ranking system, moving up through grades like T300, T700, T800, all the way to T1000, each one representing a genuine leap in how much load the fiber can bear before it fails. China's carbon fiber capabilities have scaled from T300 up to T1000 in recent years, with each grade adding a new layer of raw performance. T200 is the newest, strongest link in that entire chain, and reaching it isn't like upgrading a phone's camera resolution. Getting from one T grade to the next requires reworking the fiber's internal molecular alignment at a scale measured in nanometers, and getting it wrong even slightly means the fiber snaps under load instead of holding. Here's why nobody solved this sooner, and it's worth understanding, because this wasn't a case of China stumbling onto something nobody else had tried. High-end carbon fiber manufacturing has been dominated for decades by a small handful of companies, mostly in Japan and the United States, protected by tightly guarded manufacturing processes that took those companies decades to refine. Producing carbon fiber at these strength grades isn't just a chemistry problem. It's a precision manufacturing problem requiring exact control over temperature, tension, and molecular alignment across kilometers of fiber at a scale where a tiny inconsistency early in the process compounds into a structural weakness by the time the fiber reaches full length. Countries and companies without decades of accumulated manufacturing know-how simply couldn't replicate it, no matter how much they understood the underlying chemistry on paper. China spent years working up through T300, then T700, then T800, then T1000. Each step forcing its manufacturing base to solve a slightly harder version of the same precision problem, until it had enough accumulated expertise to attempt T1200 at industrial scale, not just in a research lab. And that distinction, industrial scale versus lab demonstration, is the actual headline here, even though it sounds less dramatic than a flashy strength number. Plenty of research labs around the world have produced small batches of ultra-high-strength carbon fiber for testing purposes. What China achieved is becoming the world's first to mass-produce T200 grade carbon fiber specifically, meaning this isn't a fragile lab sample. It's a material a factory can now reliably churn out at commercial volume. That's the difference between a scientist proving something is theoretically possible, and an engineer being able to actually order enough of it to build something real. So what does build something real actually look like with a material this strong and this light? This is where the story stops being abstract materials science and starts being genuinely relevant to industries most people interact with without ever thinking about the raw materials underneath. The material's unique combination of high strength and low density makes it a transformative backbone for diverse industries, serving as a high-tech foundation for the next generation of energy and transport. With lighter, more durable components, the fiber could enable safer high-pressure hydrogen storage tanks, extend the range of electric vehicles, and support the growing low-altitude economy of drones and flying taxis. Its versatility extends further into robotics and into the production of featherweight medical devices and elite sports gear. Let's break a few of those down individually, because each one is its own genuinely significant shift. Hydrogen storage has been one of the quiet bottlenecks, holding back wider hydrogen vehicle adoption. Remember, we've covered this before with Honda's hydrogen fuel cell story. Hydrogen has to be stored under extremely high pressure to be practical, and the tank holding that pressurized gas has to be strong enough not to fail catastrophically, while ideally not weighing so much that it defeats the purpose of using a lightweight fuel in the first place. A carbon fiber this strong, at a quarter the weight of steel, is close to an ideal material for exactly that job. Tanks that can safely hold higher pressure hydrogen while adding far less weight to the overall vehicle. Then there's electric vehicles, where weight is one of the single biggest levers determining how far a battery pack can actually take you. Every kilogram an automaker can shave off the chassis, the body panels, or the structural components is effectively extra range they don't have to buy by cramming in a bigger, heavier, more expensive battery. A carbon fiber this strong lets engineers build structural components that weigh a fraction of their steel or aluminum equivalents without sacrificing the crash safety and rigidity a vehicle chassis actually needs. And then there's the category that sounds the most like science fiction, but is quietly becoming a real Chinese industrial priority: the low-altitude economy. Essentially the broader push toward drones and short-range flying taxis operating in urban airspace. Every one of those vehicles lives or dies, literally, on its power-to-weight ratio. A flying taxi built from a material with a quarter the density of steel and multiple times the strength doesn't just fly more efficiently, it can carry more payload, more battery capacity, or both, using the exact same amount of power. If China is serious about building a genuine urban air mobility industry over the next decade, and its investment in this exact sector suggests it is, having a domestic, mass-producible, ultra-high-strength carbon fiber supply is close to a prerequisite, not a bonus. Now, here's the part of the story that connects this material breakthrough to something much bigger than one factory's production numbers. In recent years, the T-grade hierarchy in carbon fiber has become something close to a standard for measuring how advanced a nation's manufacturing base really is, the same way node size became shorthand for measuring how advanced a country's semiconductor industry is. For decades, the countries capable of producing the highest T-grade carbon fiber at scale were a short, exclusive list, and that list determined who got to build the lightest, most efficient aircraft, the most advanced defense hardware, and the most competitive high-performance sporting goods, without depending on an outside supplier who could, in theory, cut off access at any point for political reasons. That last part isn't a small detail. High-strength carbon fiber has genuine defense and aerospace applications, and materials at this performance tier have historically been treated similarly to advanced semiconductors, something governments actively restrict from export to rival nations, precisely because of what they enable militarily and industrially. A country achieving domestic, mass-scale production of the newest, strongest grade doesn't just save money on imports. It removes a leverage point that other nations could otherwise use against it. Let's be honest about the limits here too, because a genuinely strong story doesn't need exaggeration to hold up. Manufacturing a material at the T1200 grade doesn't automatically mean every industry mentioned so far, EVs, hydrogen tanks, flying taxis, immediately switches over to using it tomorrow. Carbon fiber, even at massive industrial scale, remains significantly more expensive to produce than steel, and integrating it into existing manufacturing lines built around metal stamping and welding requires real retooling, real engineering validation, and real time. This material is genuinely transformative for applications where weight savings translate directly into performance or cost advantages large enough to justify the price premium, aerospace, high-end EVs, hydrogen infrastructure, defense hardware. It is not, at least not yet, on a trajectory to replace steel in something like a bridge girder or a shipping container, where raw material cost still dominates the decision far more than weight does. But that nuance doesn't undercut the actual significance of what happened here. It sharpens it. This isn't a story about carbon fiber replacing every steel object on the planet overnight. It's a story about one of the most tightly guarded, most strategically important advanced materials in the world, a material previously dominated almost entirely by a handful of Japanese and American manufacturers, now being mass-produced domestically inside China, at a performance grade the rest of the world hasn't matched at scale yet. Every industry that depends on strength-to-weight performance, from electric vehicle range to hydrogen storage safety to the entire emerging flying taxi sector, just gained a domestic supply chain option that didn't reliably exist before this announcement. So here's the actual question worth sitting with. For decades, the countries that controlled the world's most advanced carbon fiber also controlled who got to build the lightest planes, the most efficient rockets, and the most advanced defense hardware, without ever needing to ask anyone else's permission. Now that China can manufacture that same top-tier material at industrial scale on its own, the real question isn't whether this replaces steel in your kitchen appliances next year. It's how much of the next decade's aerospace, EV, and defense manufacturing quietly shifts toward whichever country controls this exact supply chain, and whether the rest of the world is racing to catch up or has already fallen a T-grade behind.